We have pulverized coal, which we can simplify it and assume it to be carbon, although it can consist of some other elements as well, such as sulfur, for example. But here, let's assume it's just carbon. Okay, so pulverized coal, it's entering a combustor or a combustion chamber at the state 298 Kelvin and 1 atmospheric pressure, which is sort of the reference state, and it is going to burn completely with oxygen, which is entering at 400 Kelvin and 1 atmospheric pressure. So oxygen is entering at slightly higher temperature. Now a stream of CO2 is formed, of course, by the reaction of carbon with oxygen, and the stream of CO2 actually exits at 500 Kelvin at the same pressure. Okay, so for the control volume that's at steady state, which is enclosing the reactor, this thing right here, we need to evaluate the rate of heat transfer in terms of kilojoule per kilomole of coal that's entering. Okay, so we're just not interested in heat transfer, but heat transfer per unit mole of coal that's going into the system. We can assume the ideal gas model for oxygen and CO2, which means that we can make use of the ideal gas tables for these. And also we can neglect the kinetic and potential energy effects. Okay, so this is the reaction that we're dealing with. 1 mole of carbon reacting with 1 mole of oxygen, giving 1 mole of CO2. Okay, and all what we are trying to do is we want to calculate how much heat we need to extract or how much heat we need to add, so that for the reactants that we send at this state, 298 Kelvin for carbon and 400 K for oxygen, these two after reaction they produce CO2 at 500 Kelvin. Okay, so this is what we are trying to ask. Now to bring it more close to real life experiences, I mean, here we're talking about burning coal, right? So the charcoal or the coal that you burn for barbecue is something similar. It's going to consist mainly of carbon, although it may also have some other impurities. Let us neglect the impurities for now. We know that when we burn it, right, we get a lot of heat out of it, and of course one of the combustion products which come out of it, such as CO2 and others, they are going to come out at a very high temperature, typically 1000 Kelvin or maybe even 1500 Kelvin or more, right? So we can sort of, from our experience itself, we can say that, you know, if you're going to, if carbon and oxygen are going to react, whether, I mean, oxygen comes at 400 Kelvin or even at 298 Kelvin, the combustion products are going to come out at very high temperature. But here we want the CO2 to come out at 500 Kelvin, okay? Which kind of tells you that if you want CO2 to come out at such a low temperature, you'll have to reject heat from the system. You'll have to somehow take out a lot of heat. And so even before solving the problem, we sort of know that heat is most likely going to be rejected, right? We don't have to supply any heat to get 500 K. If we do not reject heat, in fact, we will not be able to reach 500 K. So this is the sort of intuition that I want you guys to be having while starting to solve a problem itself. Of course, you can't have it for all problems, but whenever possible, try to have that intuition, so that when you plug in the numbers and get an answer, the answer should make sense. Okay, because it's not just a matter of plugging in the numbers and getting it. Sometimes you plug in the numbers, there are calculation mistakes, and if you do not have a physical understanding of what's happening, you may just give a wrong answer and you may think it's fine. So it's really important as engineers to have that physical understanding. Okay, so now let's go ahead and try to apply energy balance to this and try to solve this problem. Now this is the problem that we're dealing with. This is the reaction that we're dealing with, and the way we are going to apply the energy balance is pretty straightforward. It's just the same way that we have applied the energy balance till now. We're dealing with a steady state, steady flow system, right? So of course there will not be any change in the energy, and all the energy, energy that's coming in minus energy that's going out is going to be equal to 0. So heat N, which is basically what Q dot CV is, heat N minus work out plus the mole flow rate times the enthalpy of what's coming in, right? For both carbon and oxygen are the two things that are coming in, minus the mole flow rate times the what's going out, which is CO2 that's going out. Okay, so this is simply the energy balance that we write for this steady state, steady flow system. Of course, we know that there's no work done here, so this part goes down to 0. and we can write it in terms of the heat, which is what we are trying to calculate essentially. Okay, now here we just don't want Q dot CV, we want Q dot CV per unit mole of coal or per mole of coal. All right, so it's sort of what we're looking for here is not Q dot CV itself, but we're looking for Q dot CV by N dot C. Okay, what is the mole flow rate of carbon? Now, when we're looking at this equation right here, we see that 1 mole of carbon is sort of reacting with 1 mole of oxygen to give 1 mole of CO2. Okay, so we can sort of write this equation right here into, we can write it in terms of Q dot CV by N dot C, right, and sort of divide everything by N dot C on the right hand side. So we get this ratio of mole fractions times enthalpy of CO2 minus enthalpy of carbon minus this ratio of mole fraction, ratio of mole flow rates times the enthalpy of oxygen. Okay, now irrespective of what the mole flow rate of carbon is, we know that 1 mole of carbon is going to need 1 mole of oxygen and also is going to produce 1 mole of CO2. So if you have n moles of carbon, then they're going to need the same number of moles of oxygen as well, and they're going to produce the same number of moles of they're going to need same number of moles of oxygen, and they're going to produce the same number of moles of CO2. So essentially what I'm trying to tell you is, if you have NC in the inlet, it's going to require NO2. These two are going to be equal. NC is going to be equal to NO2 because it's going to require the same number of moles to react. And if you have NC at the inlet reacting with NO2, which both are equal, then they're going to produce an equal number of moles of CO2. So essentially what I'm trying to tell you is this ratio right here and right here, these two ratios are going to be equal to 1. Okay. Now, once it's equal to 1, this equation simplifies even a bit more. We are having this simply in this form, right? Q dot CV by NC, which is what we're trying to determine, is equal to enthalpy of CO2 minus enthalpy of carbon minus enthalpy of oxygen. All right, any question here? Anything that's not so clear up to this point? All right, either it's very clear or it's completely unclear. I hope it's the former. So you guys are not asking questions, so let me go on for now. Okay, so coming back to this equation, there are only 3 things we need now. Okay, we need to evaluate the enthalpy of CO2, the enthalpy of carbon, and enthalpy of oxygen. Once we have done that, our problem is solved. So let's start with enthalpy of carbon. Okay, we know that carbon enters at the standard state, which is 298 Kelvin and 1 atmospheric pressure. So now just writing the general formula for calculating the enthalpy. Enthalpy for any system would be equal to enthalpy of formation for that system plus delta H. Okay. Now here we are already at 298 Kelvin, so we do not need any delta H because delta H indicates the enthalpy change due to being away from 298, right? Enthalpy change that is due to the state being at a different state than the reference state. We don't have, we are actually at the reference state. So this delta H goes down to 0, Hc is simply equal to HF. Now HF also, enthalpy of formation for carbon, we already know from our discussion that at standard state at 298 Kelvin and 1 atmospheric pressure, the enthalpy of formation for carbon is 0. So we end up with 0 for this part. Okay, so this part is simply 0, nothing else, 0 kilojoule per kilomole. So now let's go ahead and talk about oxygen. Okay, now oxygen also we're going to use the same definition. I mean, enthalpy for oxygen at 400 Kelvin and 1 atmospheric pressure is going to be equal to its enthalpy of formation at the standard conditions, 298 K, 1 atmospheric pressure, plus the enthalpy difference between the temperature we want minus 298 Kelvin. So what is the temperature we want? It's temperature we want is 400 K. Okay. So here you could actually go directly to table 823, which lists the ideal gas properties for oxygen. And we already mentioned the question that we are going to treat oxygen as an ideal gas. Okay, so here the first part, the enthalpy of formation, it's already given here, so you could just pick it up from here instead of going to table 825. So the first part is 0. The second part is delta H, right? How much is the enthalpy change between the state you want, which is 400K, minus the state corresponding to the reference state, which is 298K. So we just need to take a difference between these two values, 11,711 minus 8682. That is the difference in enthalpies that we're looking at. Okay, so enthalpy of oxygen would simply be equal to 0 plus this value, so it comes out to be 3029. So that's it. That's about the enthalpy for oxygen. Now the same way we will calculate the enthalpy for CO2 as well. Again, we know the temperature that we are looking at. Okay, and again, it's the same formula. Enthalpy for CO2 at any given temperature and pressure would be equal to enthalpy of formation plus the delta H. Okay. Again, we go to table 823, which lists the ideal gas properties for CO2 as well, and it also has HF naught. So HF naught this time is not 0. Okay, we got to take this value plus the difference between the enthalpy at the state we want, 500K, minus the enthalpy of the reference state, which is 298. So again, it's minus 393,520, which is the enthalpy of formation of CO2, plus this value right here, 17,678, indicating the enthalpy at 500 Kelvin, minus the enthalpy at the reference state, 9364. So now what we have done by including this enthalpy of formation in all of these calculations is that we have defined a common reference point. So the enthalpy of CO2, C, and O2 can be compared on the same pedestal. Okay, they're all they are comparable. They're compared to the same reference point now. So this is the value that we get for enthalpy of CO2. So now it's just a matter of plugging in these numbers here. Okay, we have the numbers. This is for CO2. This is for carbon. This is for oxygen. And when you plug in these numbers, it comes out to be minus 388,235 kilojoule per kilomole. And this negative sign simply indicates that we have to reject some amount of heat to have CO2 at 500K, which is something that we knew from the beginning.